So yes, I will give you an overview now of the policy brief, so you don't have to read it if you don't want to. And the topic is, as Ilona mentioned, is there conflict between the clean air goals of the European Green Deal and climate neutrality? And I have, together with the contributing authors below, put together this policy brief. So what we want to answer in the brief is basically these three questions. First of all, why is there a potential conflict between the goals that are mentioned in the European Green Deal? So that has to do with climate and clean air. And here we, as Ilona mentioned, will talk about the two-sided role of aerosol particles. And we will also then explain what are these aerosol particles and what effects do they have on climate. So how do they cool and how do they warm the Earth? And then what is the relevance for policy? And here's the discussion, I think, that will come in later and talk about that. So first of all, why is there a potential conflict? And that is basically illustrated in the figure to the left, and I will walk you through that. But first of all, what is an aerosol particle? So aerosol particles are suspensions of tiny solid or liquid particles in air. And they are from about a nanometer in size to tens of micrometers. So you can't see them with the naked eye, but they exist around you in quite high concentrations. So if you would breathe in some air now, you would breathe in also thousands of particles. Most of them would go out again when you breathe out, but some of them will also stay in the lungs. So these particles can be emitted or formed both from natural sources and from anthropogenic activities. And natural sources are, for example, oceans. So when you have sea spray or waves that break, you will generate sea spray. And you can see it if you stand next to the ocean side on a stormy day. You can see this haze, which is basically the aerosol particles that are humidified. Deserts are also sources of particles. So the sand that is blown up from the deserts, that's also aerosol particles. But here we will focus on the anthropogenic aerosol particles, so that are formed from different activities that are illustrated here to the left. So for example, traffic, different types of fuel burning, so biomass burning, agriculture and industry. So when these particles are emitted, as we can see here in the figure that shows the industry activity, you can almost see that they have an effect on buildings and material, and they have an effect on the environment. They are contributing to the problem of acid rain, for example. They can also cause plant damage and other problems. But as I mentioned before, that when you breathe in air, you also breathe in these particles. And if there are high concentrations or if there are different harmful materials in the aerosol particles, they can cause respiratory and cardiovascular diseases. And this contributes then to the problem of air pollution that globally contributes to about 4 million deaths per year. Actually, for 2019, I think the number is 6 million people that die prematurely because of air pollution. And these particles are then a substantial part of the air pollution. So governments and countries, they want to reduce the amount of particles in the air, of course, to generate better air quality and health. But then there's the small issue that aerosol particles, they also have an effect on climate. On general, they have a cooling effect on the Earth. So as we emit anthropogenic particles, we mask or hide some of the greenhouse gas warming that we would have had at the same time. So if we start to reduce the amounts of aerosols in the atmosphere, that may also imply a climate penalty. And this is then the potential conflict that exists between the health effects and the climate effects of aerosols. So how do the aerosol particles then affect climate? Well, a bit simplified, one can almost see it here in this picture. So this is over Indonesia during the biomass burning season. And we can see this haze within the boundary layer of the atmosphere. And the haze will then both reflect some of the sunlight that comes in towards Earth and would normally heat the Earth, and it will also absorb some of the sunlight within the atmosphere if we have a certain type of aerosol particles that absorb sunlight. The aerosol particles, they will also affect how cloud forms. So for each cloud droplet that exists in the atmosphere, there is an aerosol particle. Otherwise, the cloud droplets wouldn't form. And in general, one can say that if we have more aerosol particles, we get more cloud droplets. And this will make the clouds look brighter if you look at them from above. They will reflect more sunlight because you have smaller and more numerous cloud droplets, which makes the cloud optically thicker. And this will also in turn affect precipitation and other processes. So in general, one can say that the aerosol particles, they prevent sunlight from reaching the surface, and that is why they mainly cool the climate. But because some of the aerosol particles also absorb sunlight, they can heat the atmosphere, and sometimes that heating can also reach the ground. So how big is this effect? Well, the IPCC, so the Intergovernmental Panel on Climate Change, they do a compilation of the current research about every 8 years or so. And this is from their latest compilation. And you can see here different components. So greenhouse gases, other anthropogenic, total anthropogenic and natural variability, and the climate effects in watts per square meter. And to the right, we have warming effects, and to the left, we have cooling effects. So if we start here from the top of this figure, we can see that greenhouse gases, so carbon dioxide, methane, and nitrous oxide, and halocarbons, they warm the climate on average, as a global average. And the warming is about 2.8 watts per square meter. If we then go to the next row, we have something that is called here other anthropogenic. And this is mostly aerosol particles, but not only. There's also ozone and land use change, for example. So on average, as a global average, the aerosol particles, they cool the climate about minus 0.8 watts per square meter. But there's a large uncertainty range here. So we actually don't know if the aerosols cool the climate a lot, or if they actually warm the climate slightly, that we have a lot of these absorbing particles in the atmosphere, and therefore they warm the climate. And if we then look at the total anthropogenic forcing, we can see that it's about 2 watts per square meter, but there's a large uncertainty, and this uncertainty mainly then comes from the aerosol particles and their climate effects. And this has important implications because it means that if the aerosol particles cool a lot, so if this is their true climate forcing, then we mask currently a lot of the greenhouse effect. And if we remove the aerosol particles, we would suddenly then get more warming. If the aerosol particles have a small or even positive effect, we wouldn't see much difference if we remove the anthropogenic aerosol particles. So why is there such a big uncertainty? Well, there's no easy answer to that, but there are many contributing factors. So first of all, as I mentioned in the beginning, there are many types of aerosol particles, or there are many sources and therefore many types of aerosol particles. We have the natural aerosol particles and we have the anthropogenic ones. So natural, for example, sea spray from the oceans, dust from deserts, sulfate from volcanoes, organic carbon from plants. Anthropogenic ones, we have nitrate from agriculture, sulfate from combustion, soot from combustion, and soot and organic carbon from fires. So these are examples. So the chemical composition is very complex, and it differs depending on where you are on the Earth. And as I mentioned, most aerosol particles, they cool the climate, but some warm the climate. So if we look here at the warming aerosols, so typically that is soot from combustion, or soot and organic carbon mixed from, for example, fires. Other aerosol particles that cool is, for example, nitrate and sulfate, and also pure organic carbon will cool the climate. So the aerosol particles, they stay on average a few days in the atmosphere. So that makes them different from greenhouse gases that stay almost forever in the atmosphere. So if we go to one location at a certain time, we will have a very different aerosol population compared to if we go to another place at a different time. So this is an animation from NASA, and it shows a mixture of satellite data and modeling, climate modeling. And they have simplified the aerosol types here so that you in red, orange see what they call dust. In green, you see soot and organic matter, so that is from biomass burning. In white, you see sulfate, so that is mainly anthropogenic industry. And then blue, that is sea spray or sea salt. So we can see here that over Europe, it looks like sulfate is mainly dominating together with sea spray. And this is not completely true. We also have a lot of organic carbon. It is just not modeled very well by this model. But the overall point is that we have a complex mixture, and we have a large space and time variability of the aerosol particles. Another thing that complicates the climate effects of aerosol particles is that the paths from emission to aerosol formation and then to the climate impacts, these paths are very complex. And I wanted to focus here on the fact that we have the sources here of different aerosol particles. And sometimes the particles are emitted directly as these particles into the atmosphere. But sometimes it is gases that are emitted to the atmosphere, and they will, after some chemical reactions, form condensable vapors that can contribute to aerosol formation. And this will then give us the total atmospheric loading. And through some complex interaction with clouds and other things, they give us the total radiative forcing and the climate response. And similarly, also the air quality response. So this is part of the reasons why there is such a large uncertainty here in terms of the aerosol climate effects. But nevertheless, we know a little bit. We know that they, on average, most likely cool the climate. And we know a few other things as well. And I would like to summarize these things in the next slides. So we can look at historical emission trends in aerosols and aerosol precursors, and from that also use models to understand what the climate effects are. So here I show you the 4 most important anthropogenic aerosol types and their evolution from 1900 until 2015. And to the left you have the global emissions, and to the right you have the European emissions. Soot is shown as black lines and gray organic carbon as gray line. And these are direct aerosol emissions, so emitted directly as particles to the atmosphere. And you see the amount here to the left for these 2 aerosol types in petagram carbon per year. The other 2 aerosol types, sulfate and nitrate, they are not emitted directly. They are emitted first as precursor gases that then form the aerosol particles. So here we show the aerosol precursor gases, so sulfur dioxide in red and nitrogen oxides in brown. And you see the scale here to the right in petagrams SO2 or NO2 per year. And you can see that the scale is very different. It's much larger here, but that does not necessarily mean that there are more aerosol particles, because these are the gases that are emitted first that are then eventually converted into aerosol particles. So it's difficult to compare the absolute numbers here. But we can look at them in terms of their trends, and also I will tell you a bit about their climate impacts as far as we know. So sulfate that forms from SO2 is the particle type that has dominated the anthropogenic aerosol particle burden historically. So the sulfur dioxide emissions and the sulfate concentrations, they have increased during the 20th century until about 1980. And due to different agreements internationally about air pollution, and also due to the disintegration of the former Soviet Union, emissions then started to decrease drastically after 1980, mainly in Europe and in North America. And you can see here that the emissions over Europe, they went down by to almost, they went down almost by 70% from 1980 until 2000. But the increase historically from 1900 until 1980 also meant increase in global cooling that has then masked some of the anthropogenic greenhouse effect. After 1980, the emissions started to decrease, but not as much as we see here for Europe. And the reason is that emissions started to increase instead over Asia after 1980. So they have continued basically to increase after 1980 until at least 2010. Since 2010, there has been a slight decrease over East Asia or a large increase. We are actually not completely sure at the moment. But this has then also then implied that there has been a decrease in the global cooling after 1980, and the anthropogenic greenhouse effect has been unveiled, one can say. It is not masked anymore by the sulfate. Soot emissions. So soot is a relatively small contributor to the global aerosol burden compared to sulfate, but it is efficient at warming. So even if the amounts are small, it can still warm quite efficiently. So soot emissions have increased steadily over the whole 20th century and also the beginning of the 21st. And this has then meant a small but steady increase in warming. And the largest source region of soot aerosols is really Asia. So this is where we see the largest increases also now, in particular over Southern Asia. Organic carbon has contributed relatively little to the total anthropogenic aerosol burden as well, at least compared to sulfate, but there's a large uncertainty associated with organic carbon. For organic carbon, we see a slow but steady increase, just as for soot during the 20th century and the beginning of the 21st century. And this has also meant a small but steady increase in cooling. It should be here. I have written the wrong thing. So organic carbon cools the climate. Sorry about that. Nitrate from NOx, so that is the brown lines, has also increased steadily during the 20th and 21st century. And it is now actually what we think is the second largest anthropogenic aerosol component after sulfate. But nitrate has very complex formation paths, and it's very difficult to predict. So we are very uncertain about how much there is actually in the atmosphere and how big is the climate effect from nitrate. And there's a lot of nitrate aerosols, particularly over Europe, Asia, and the US. So what about the future then? What will happen in the future? So here I show you to the left the global emissions of the 4 different aerosol types, and to the right the European emissions. But I will focus here on the global emissions. And there are 2 emission scenarios here for the future from 2020 to 2050. So the dashed lines here, they show a high aerosol emission scenario. So what we think is going to happen if we don't do anything about the air quality issues, basically, so that we continue with the current legislation that we have in terms of air pollutants. The full lines here are emission scenarios if we really drastically decrease aerosol emissions because of the pollution issues that we have. So for all of the 4 aerosol types, we will then see decreases in the aerosol emissions. So what we can say is that in general, emissions of sulfate from SO2, soot, and organic carbon, they are expected to either stay approximately the same here according to this high aerosol emission scenario, or they're expected to decrease. And we think that the decrease is more likely actually in the future. Nitrate here, we have also shown that, oops, sorry about that we expect nitrate to decrease in the future or stay constant. But nitrate is much more uncertain than the other aerosol components. We actually don't know really what's going to happen with nitrate in the future. So what will then be the future climate penalty of these aerosol emission trends? Will it have any consequences for the, for example, the Paris Agreement that we are trying to achieve? So first of all, I wanted to point out that we see here that either the aerosol emissions will decrease for most of the aerosol components, or they will stay about the same. And because we have decreases in the future of both sulfate and organic carbon, and also by soot, these aerosol components seem to balance each other quite well in the future, so that we don't get a large climate penalty. But it, of course, assumes then that the aerosol emissions follow these different emission scenarios. Another thing that we can see here from the picture of the global and future emissions is that even if we take here sulfur dioxide, so the red line, and look at the more drastic decrease, it is not a very big future decrease that will happen according to this maximum feasible reduction scenario. And therefore, we also think that the largest reduction in sulfate has already occurred. But I have put a little question mark here, and that is thanks to Björn and others that have pointed out a small inconsistency that maybe some of you have noticed if you pay really a lot of attention. If we look here at sulfur dioxide in 2015, the emissions here, according to the past historical emission data, is somewhere around 115 petagrams SO2 per year. And then if we go to the future here, and you have the scale here to the right, we can see that it starts here in 2020 at about 50 petagrams SO2 per year. So we have suddenly this drastic decrease between 2015 and 2020. And I should say that the left emission scenario and the right one, they come from different sources. And this is one reason for the discrepancy. But it is also because we actually don't know very well what has happened here between 2015 and 2020. So different emission inventories, they actually disagree on the extent of recent emission reductions in particularly SO2, but also soot and other aerosol types. But there are some observational evidence that support that there has been rapid emission reductions in East Asia. So that this future emission scenario here or here is actually the one we should look at. And taken together, this means that we think that the future climate penalty is most likely small, both because of the fact that the largest emission reductions have probably taken place, and secondly, because we think that the reductions in sulfur and soot and organic carbon will to some extent compensate each other. So then I have come to the answers that we have given to the questions that were raised in the beginning. So why is there a potential conflict between climate and clean air goals? And this is the two-sided effect of aerosols, that a reduction in the amounts of aerosols in the atmosphere would benefit global air quality and health. But at the same time, it can unveil some of the global warming, as we have had a net cooling of aerosols of the climate. What is known about the cooling and warming effect of aerosol particles? Well, we are pretty sure that the sulfur emissions, so sulfate aerosols, have dominated the aerosol burden and cooled the climate globally with the largest cooling between 1960 and 1980. And thereafter, the cooling has been reduced as the sulfur emissions have also been reduced. And therefore, we think that the future aerosol reductions will mostly give a small climate penalty, because the largest reductions have probably already been made. And also the sulfur reductions will to some extent be compensated by reductions in soot. So what is the relevance then for policy? Well, even though there is a small climate penalty in the future, it can still have some drastic consequences for the success of the European Green Deal and the Paris Agreement. If the climate effect of the aerosol particles in the future will be about 0.5 degree, it can still have a large impact then on if we make the 1.5 or 2 degree target. And overall, we would like to emphasize that reducing carbon dioxide emissions is the most important climate action. And regarding the uncertainty in terms of aerosol particles, this is something that we work on within Forces. So here you can see a schematic of the Forces project, where we look at all of these complex processes in terms of emissions and effects on clouds and removal. And the objective is then to provide better Earth system models and reduce the uncertainty in climate forcing, and get a better quantification of the near-term climate response to aerosol emission changes. And please have a look at our website, and also we would be happy if you get in touch with us and ask questions if you have any. So, thank you.